Okay, my friends, so I want to return back to our first example for today, just to show you the effect that a sample size can have on significance. Now, this is probably going to make sense to you hearkening back a couple weeks, because as you increase the sample sizes on confidence intervals, margins of error shrink. And the p-value is effectively the same, it's operating in the same way as the margins of error for a confidence interval. So as we get larger and larger samples, the precision of our estimates gets better and better. So this was the first one. This was the one about flu vaccines. And we tested 500 people with a new flu vaccine. 50 of them got the flu, and we said, okay, that's 10%, right? 10% is less than 12%, which is the assumed population parameter. But unfortunately, the p-value was large, quote unquote, above 5%. So we said, well, it's lower. 10% is lower than 12%, but not statistically significantly lower. Now, what happens, and this is definitely a what if, it's very, very much conditional on, what happens if we were to increase the sample size, say to 600, and then simultaneously get 60 people have the flu? Now the reason I picked those numbers is that still maintains a sample proportion of 10%. But now please notice the p-value got smaller. It's still not below 5%, but it's gotten smaller because the drop in the rates of those getting flu, the 10%, now looks more significant than it did before. What if 70 out of 700, which would again still maintain the 10% sample p-hat? Now your p-value is just around 5%, still too large by the strict 5% guideline. But let's make it work. Suppose you have 100 out of 1,000. Now your p-value has dropped below 5%. Please realize, in every single one of these cases, the sample proportion was 10%. But because you saw that 10% on a larger and larger sample, the central limit theorem is kicking in, the precision is getting greater, and the difference is getting more significant. Now here's the kind of cool intersection between mathematics and statistics. Let's back up again, back to what it was originally. Okay, let's say it was 50 out of 500. But let's suppose it was 55 out of 500. Now, why did I pick 55 out of 500? Well, 55 out of 500 is 11% of a sample proportion. Now, 11% is still less than 12%, but it's not statistically significantly less. It's only 1% difference, right? And over a sample of size 500, that is not statistically significant. But what if we were able to get 110 out of 1,000? That is still a 11% sample statistic. But do you see how the p-value went down again? And now let's suppose you were able to get 220 out of 2,000. Once again, you end up with a p-hat of 11%, but now the p-value is dropping more and more. How about 330 out of 3,000? Look at that. Still 11%. But now that 1% difference between the vaccine flu rate and the non-vaccinated flu rate is statistically significant. All right, one last little video to wrap this whole thing up. Mathematically, you can make any result that you get in a study statistically significant. All you've got to do is get a sample size large enough to drive that p-value down. Now, that's easier said than done. I was operating a little bit fictitiously in the Excel calculator just now because I kept maintaining that same p-hat value and just increasing the sample. That's probably not going to happen in reality. But the underlying truth is, if you get a large enough sample, any percentage difference between a p-hat and an assumed population parameter proportion can be shown to be significantly different with a large enough sample. But here's the problem. Suppose your p-hat is 11.9% and the assumed population parameter is 12%. Okay, that's a 0.1% difference. You can make it statistically significant if you get a large enough sample, but is it practically significant? There is a difference between statistical significance, which is purely mathematical, it's based in the computations of hypothesis tests, and practical significance, which is what people become experts in their fields later. For example, a flu vaccine researcher might take one look at what we just did and said, oh, that's great, you showed a statistical significant difference of 2%. We don't even market these things unless it drops at least 5. In which case, it doesn't matter that it's statistically significantly lower because it's not low enough. So, statistical significance, purely mathematical, has nothing really to do with the context of what you're talking about. It's based on hypothesis testing. Practical significance, which we can't really talk too much about in here because we're not experts in all fields. I'm not an expert in pediatrics or flu vaccine virology. Best we can do is work on the math, get the math solid, and then if you take more statistics classes, which I hope you do, I hope you take research methods classes and maybe Stat 2 if we even offer that again, you learn the ins and outs of the practicality. But for right now, I just want you to drive home the point that we can measure statistical significance, but that isn't necessarily the same as practical significance. Okay, my dear friends, I think it's time to try the next homework.